So today I will now speak about weak convergence. We will be working on X, a normed linear space. And let me define weak convergence. We have a sequence xn, xn in X. We will say that xn converge weakly, and that will be represented by this half arrow to X if for all bounded linear functional, so for all L in X prime, L of xn converge to L of X. So a sequence xn would be said to converge weakly to X if whatever bounded linear functional defined in X, the sequence of real numbers or complex numbers L of xn converge to L of X. We have, so that's called weak convergence. Strong convergence, which is represented by the full arrow, xn to X, this means that the norm of xn minus X converge to 0. Okay? And what I claim is that if you have a sequence xn converging strongly to X, then xn converge weakly to X. So strong convergence implies weak convergence. And this is more or less obvious. So assume that xn converge strongly. So this statement holds. Now, if you want to prove that you have weak convergence, we have to show that this happens for all bounded linear functionals. So fix a bounded linear functional L. Consider L of xn minus L of X. By linearity, this is equal to L of xn minus X. We have seen that this is bounded by the norm of L times the norm of xn minus X. Since xn converge strongly to X, this norm converge to 0, and therefore the sequence L of xn converge to L of X. So the converse is not true. So we have seen that if xn converge strongly to X, then xn converge weakly to X. Well, my second observation is that the converse is not true. And let's prove that. So let me give you an example. So recall that we represent by L2 the space of all sequences AJ, J larger than 1, such that AJ, let me take AJ in R for this example, and I'm assuming that AJ is square summable, which means that the sum for J larger than 1 of the square of the absolute value of AJ, that this is bounded. Okay? So we have seen that L2 is a Hilbert space. We know that it's a Hilbert space. And therefore, in Hilbert space, if you take L, okay, let me take M, a bounded linear function in L2. So this is an element of L2 prime. We know that there exists B in L2 such that L of A is equal to the scalar product of B with respect to A. Or, well, here we are in real space, so I don't care of the order. And remember that the scalar product is defined as the sum of AJ times BJ. Fine. So now let's consider the following sequence. So I take xn. So these are elements of L2. So for each n, we have a sequence xn1, xn2, and so on. And what's the sequence xn? Well, it's just the sequence in which you have zeros until the nth position in which you have a 1. So this is at the nth position. So on the one hand, what I claim is that xn converge weakly to 0, and xn doesn't converge strongly to 0. That xn doesn't converge strongly to 0, it's easy because, well, you just take the norm of xn in L2. So let me take the norm square. The norm square in this space, it's given by the scalar product of xn with xn, which is the sum. And you see that by definition of xn, this is constant equal to 1. So that's clear. It's clear that xn does not converge to 0 strongly. Now let me show that xn converge weakly to 0. For that, you need to fix a bounded linear functional, call it M. By the Riesz representation theorem, you know that there exists an element of L2, which I'm calling B, such that M applied to any element A, it's the scalar product of A with B. Therefore, if now I apply that to xn, so this is the scalar product of B with xn. By definition of xn and by definition of the scalar product, this is equal to Bn. So B, it's a sequence, B1, B2, etc. And the scalar product of B and xn just gives you the nth coordinate of Bn. Now, B, it's an element of L2, which means that Bj square, the sum for j larger than 1, that this is finite, because it's an element of L2. Since it's finite, it means that Bj square converge to 0, and therefore, from that, we get that indeed Bn, so M of xn, converge to 0. So we just proved that M of xn converge to 0, and this is equal to M of 0. And this proves that xn converge to 0 weakly, because for any bounded linear functional M, M of xn converge to M of 0. So now let me give you a second example in which we have a sequence which converge weakly but does not converge strongly. So for that, I'm taking X to be the space of real valued continuous functions defined on the interval 0, 1. So these are all functions defined on 0, 1, which take real valued and which are continuous. And the norm of this space, X, is just the supremum of xt for t between 0 and 1. And I want to consider in that space the following sequence, xn, for n larger than 1, which is defined as follows. So here is 1, 1, 0. So let me take here 1 over n, 2 over n, and the function will be equal to 1 at 1 over n, 0 at 0, 0 at 2 over n, actually 0 in the interval 2 divided by n up to 1, and linear in these two intervals. So here is the graph of the function, and if you want it defined, so x and t will be n times t for t between 0 and 1 over n. Then 2, I guess, minus nt for 1 over n less than t less than 2 divided by n. So let's see if my definition is correct. If t is equal to 1 over n, this is 1, so I get 1. And if t is 2 over n, I get here 2. This is 0, so that's fine. And t, and 0 for t between 2 divided by n and 1. So this is the formal definition of my sequence xn. These functions are continuous. And what I claim is that xn converge weakly to 0, but xn does not converge strongly to 0. So this is what I want to prove. That xn doesn't converge strongly to 0, it's clear because, well, if you take the norm of xn minus 0, this is equal to the norm of xn. And by definition of the norm, you see that the norm of xn is equal to 1. So it's clear that xn does not converge to 0. And what remains to be done is to show that xn converge weakly to 0. And to prove that xn converge weakly to 0, we will proceed by contradiction. So I will assume that it doesn't converge to 0. And I will get from that a contradiction. So what does that mean that xn doesn't converge to 0? Well, it means that we can find a bounded linear function L such that L of xn does not converge to 0. Does not converge. So to say that Lxn, so this is a sequence of real numbers, it doesn't converge to 0, this means that there exists a positive delta and a subsequence nk such that L of x nk, it's bounded by below by delta. That for all k. Well, if this is always true, then either L of x nk it's larger than delta for infinitely many k's, or it's bounded below by minus delta for infinitely many k's. So I will assume that L of xn it's bounded below by delta for infinitely many k's, and what I'm doing rename this k so that this holds for all k's. And you'll see that the argument I'm using by assuming that it's larger than delta works also if I assume that this is less or equal than minus delta. So I will assume from now on that I have this inequality, and I will also need a property of this sequence nk. I will assume that nk plus 1 it's larger or equal than, or maybe strictly larger than 2 times nk. Okay. Well, so it's clear that if this is not the case, you can just rename the nk, so you can just drop some elements of your sequence to get a new subsequence which satisfies this inequality. Right? So if this is not true, you can just drop some terms of your sequence and get a new sequence for which this inequality always holds. So I'm assuming that nk plus 1 it's strictly greater than 2 times nk, and that Lxnk it's larger than delta for all k. You see that from this inequality, what I get is that 1 over nk plus 1 it's smaller, or 2 times nk plus 1, it's smaller than 1 over nk. So this is the inequality I will be using in my argument. And with that one. So this is what we need. So let's proceed. let me define ym. So this is a new function, which is equal to the sum from k going from 1 up to m of x and k. And what I claim is that ym, so I want to prove that ym is bounded by 3. The uniform norm of ym, uniformly in M, this is bounded by 3. And for that, I won't need this inequality, so I just erase it, but I will need it later. And so let me prove that ym is less or equal than 3. So I'll draw a picture to convince you of that. So let me start with an m. So here is, let's say, 1 over an m, 2 times over an m, and this is 1. Now let me consider n m minus 1. But from this inequality, I get that 1 over n m minus 1, it's larger than 2 times, so it's larger than this term. So n m 1 over n m minus 1, it's somewhere here. And let's say that here it's 2 times n m minus 1. And now if I apply this inequality for k plus 1 equal to m minus 1, what I get is that m minus 2, 1 divided by n minus 2, it's larger than 2 times n m minus 1. So n m minus 2, it's somewhere here, and so on. So here's the function x and m. Now I have the function x and m minus 1. And here's the function x and m minus 2, and so on. And I want to bound ym, and ym is the sum of all these functions. So I will proceed by considering each interval. So first this one, then the interval 1 n minus 1 up to this one, then this one from n minus 2, and so on, up to n1. Let me also obtain here a bound of nk. So we have, I can erase the definition of the norm and the definition of xn. So from this inequality, I get that nk, it's bounded by 1/2 of nk plus 1. Okay, so this is what this inequality is telling me. If I iterate that, I get that this is 1/4 of nk plus 2. So let me write that as 2 times 2 to the power 2. So you see here that I have power 2 and 2. So if I iterate, what I will get is that this is 2p n k plus p. But I want to rewrite that as n to the power m, say, or maybe m I'm using here. So let me call that, I don't know, r. So r, it's k plus p, which means that p, it's r minus k. And what I get is that this is bounded by 2 times r minus k and r. Okay, so n, so the inequality I obtain is that nk, it's smaller than 1 divided by 2 r minus k and r. And this holds for all r larger than k. Okay? So I have this inequality. So with this inequality, I will be able to estimate ym. So let me first consider t between 1 and 1 over nm. So this first interval. In this first interval, you see that it's very easy because xn has the same definition for all t's. I erased it, but I shouldn't, so let me just recall here what was the definition of x n t. So this was nt for t between 0 and 1 over n. I won't use the other definitions, so let me just keep this one. So between 0 and 1 over n, x and t, it's n times t. So that at 1 over n, x n, it's indeed equal to 1. So now let me consider a t between 0 and 1 over n, m. So ym(t), it's equal to the sum from 1 up to m of x n k t. But in this interval, 0, 1 over nm, all x and t are defined in this way. So this is equal to the sum from 1 up to m of nk times t. So t is fixed, and t, it's bounded by 1 over nm. Now I have the sum of nk, and I will use this inequality with r equal to m. So by using that inequality with r equal to m, what I get is that this is bounded by 2 to the power m minus k times nm. So you see that 1 over nm cancels with nm, and what remains is a sum from 1 to m of 1 divided by 2 to the power m minus k. So when k is equal to m, I get here 0, m minus 1, I get here 1, up to k equal to 1, m1. So this is bounded by the sum for k larger than 0 of 1 to the power 2k, and this is equal to 2. So this proves that ym(t), it's bounded by 2 in this interval. So this is my first claim. Okay, so we proved already this bound in the interval 0, 1 over nm. So now, as I said, I will consider the interval from 1 over nm to 1 over nm minus 1. So this is So let's see what happens in this interval. Well, in this interval, there is this first piece, which is a decreasing piece, while all the other ones are increasing pieces, exactly because I assumed that this quantity is larger than this one. So since this quantity is larger than this one, I have only a piece which is decreasing. So what I will do is that, well, if t belongs to this interval, I will just bound its value, the value of the first function, so this function, x and m, by 1. So this is bounded by 1, and I'm taking here k equal to m minus m equal to m, plus the sum from k from 1 up to m minus 1 of x and kt. But for k smaller than m minus 1, in this interval, all functions are defined by this first expression. So in this interval, if I take a k which is m minus 1 or smaller, what I get is that in this interval, the definition of xn is given by this expression. So what I get here, it's a sum of nk times t. So this is bounded by 1 plus t. It's bounded by, now I'm taking, I didn't write it, I'm taking the interval nm smaller than t, smaller than nm minus 1. So t in this interval is bounded by 1 divided by m minus 1. And I have a sum from 1 up to m minus 1 of nk. And again, I will use this inequality, but now with r equal to m minus 1. So what I get is that I have r equal to m minus 1. So I get m minus 1, which will cancel with this one. And then 1 divided by 2 to the power m minus 1 minus k. So m minus 1 will cancel with m minus 1. I have a sum from k from 1 up to m minus 1. So here I have m minus 1 minus k. So when k is equal to m minus 1, I get 0. m minus 2, I get 1. So this is again a sum which is bounded by 1 plus 1 over 2 plus 1 over 4, and this is bounded by 2. So this expression here, it's bounded by 2. I have 1, which means that ym in this interval, it's bounded by 3, as I claimed. So we can proceed in this way and now take the interval n m minus 1 n m minus 2. When you take this interval, you see that now xnm is just 0, so you don't need to consider it. On this interval, all functions are increasing, but the first one, so the first one you can repeat the previous argument and just bound it by 1, and all the other ones use this definition in order to estimate. And you can repeat that for all indices, so for all intervals up to the last one, and always get that ym, it's bounded by 3. So I leave it to you to complete the details, but you can just repeat this argument to bound ym in each of these intervals, which goes from mk minus 1 up to nk minus 2, and always get the same bound. So I hope I convince you that ym, the norm of ym, it's bounded by 3. I will erase everything and just copy the bound which I erased before. So I don't need any of these. And just remember that I'm assuming that L of x and k, that this is always larger or equal than delta for all k. Fine. So I have that ym, it's bounded by 3. On the other hand, by linearity, I get that L of ym, this is equal to the sum from k from 1 to m of Lx and k. But Lx and k is bounded by delta, so I get this bound. So on the one hand, I have that L of ym, it's larger or equal than delta m, and this holds for all m. On the other hand, for this sequence ym, the absolute value of ym, the norm of ym, it's bounded by 3. So this means that L of ym, which is bounded by the norm of L times the norm of ym, that this is bounded by 3 times the norm of L. And from this inequality, what I get is that, since this is bounded by that, it's that delta m, it's bounded by 3 times L for all m, and this is impossible because delta is strictly positive, and therefore, as m goes to infinity, this quantity it's increasing to plus infinity, and therefore it will be larger, strictly larger than 3 times the norm of L for sufficiently large n. So we obtain the contradiction, which follows from the assumption that xn is not converging weakly to 0. So this proves that xn converge weakly to 0, and here we have again an example of a sequence which converge weakly to 0 but does not converge strongly.